I'm sure everyone in the audience knows after our figuring out what's going on here that today we're getting the great honor of having a seminar given by Professor Mike Sutton, who's currently at the University of South Carolina. But some of you may not know that Professor Sutton actually got his PhD here at the University of Illinois, working for Chuck Taylor. I would imagine a lot of people on this conference call are familiar with the technique of digital image correlation. You may or may not be as familiar with the fact that Professor Sutton is essentially considered the godfather of digital image correlation. I've heard this said on multiple occasions from multiple different people. I had the great pleasure of talking with him earlier. And I think you'll probably see from the presentation he's giving today, he's kind of his career has been characterized by kind of a drive for satisfying his own curiosity, and as he said, as well as when we were talking, his own stubbornness in pursuing questions until he feels satisfied with what the answers he's gotten are. And so, without further ado, I don't want to take up too much time with his introduction here, but today he's going to be telling us a little bit about applying this technique, digital image correlation in particular, to questions about manufacturing for drones.
Well, thank you, Shelley. It's my pleasure to be here, available to do this. As you can see from the title, the talk will focus on applications of digital image correlation in two areas. One of them is, as you see in the slide on the left, the wrinkling of composite toes, and on the right is a separate topic that will go toward the end, and that is the use of modern drone technology with image correlation systems to actually make high resolution, accurate measurements of deformations using drones to access locations that are typically hard to get at. So that's the background for it today. If I can go down the slide somehow. This is the outline for it. There are three basic areas that are all tied together. After the acknowledgments, we have the wrinkle measurements in thermoset toes, which is the first one. There is advanced fiber placement, which deals with actually simulating what we measured using AFP, advanced fiber placement, earlier in the first part of the talk. And then as part of the advanced fiber replacement simulations, we were going to need the mode 1, mode 2, the opening mode and shear mode traction separation laws for the toes to predict when they're actually going to wrinkle. Those three are all tied together. The latter one, the drone component of the talk, will deal with StereoDIC application, in particular for a railroad concrete tie that we measure in the laboratory, but then we can talk about how it's going to be used in a broader sense in the long term. I'll close out with some photos about the last 20, 30 years of activity that I kept and just show them to you for closure purposes. Should note that the funding for a lot of this work came from Boeing. Another part came from Ed Walton. He's the Vice President for Research and Finance. Ed Walton provided funds to build one of the components of the center that we use, center facilities we use for some of the work. In addition, the two different groups were helpful in doing much of the work. The first one, the technical support by Drs. Tadding and Gerdahl and Herrick and Rhodes and Weeby, were all for the composites. The last one, Nikos and Dimitris Rizos, were all involved in the civil infrastructure and drone work, and they were primary contributors for that. First part is the wrinkle formation in thermoset toes during advanced fiber placement. For those that don't know much about it, automated advanced fiber replacement, it was developed to speed up the process of manufacturing large-scale structures, predominantly for aerospace structures. It is used currently by Boeing in Charleston, South Carolina, as well as Seattle, to make the 787 fuselage. When it's actually in progress, it runs very fast. It runs at about 2 meters a second. So all the work that we did here was an attempt to run at similar rates to show what would happen if you tried to place something on an existing surface and race across it at high speed by pressing down on it and heating it up. Could you get it to bond without wrinkling? Unfortunately, when you do it, because the carbon fibers that are embedded in many of these are very stiff, as it tries to curve on curved paths, such as in the inside of a fuselage, cylindrical fuselage structure, they will tend to wrinkle. Those carbon fibers are very stiff, and as you try to compress them on the inside, they tend to buckle. And if you don't have a strong enough bond, the area locally will pop off and cause a wrinkle in the material, will not bond at all. So in this work, one of the first things that we were asked to do by Boeing was to develop a methodology to measure how it's deforming and the shape of the wrinkles when we actually tried to use the advanced fiber replacement process to put them on. And you'll notice throughout the talk that there'll be oval boxes with numbers in them. You can use those to identify papers at the end where we actually publish some of this work. And in the bottom right corner are page numbers I should have mentioned earlier. If you have a question toward the end, you can write down the page number and I can come back to that. And we can look at what your question is about. So continuing, the pattern development was the main part. We had to find a way to put a pattern on that we could track with the digital image correlation method. We did that by unwinding the small toes. These toes are tens of meters long, but they're very narrow. These were 6.35 millimeters wide. They're very thin, about 0.25 millimeters thick. So we unwound them slightly, we tightened them a little bit, and we sprayed them slightly with high temperature white flat paint. They're black, so you don't have to paint them any more than that. And that spray of black paint gave us a nice high contrast pattern. To make sure we didn't have reflections, we did have to put polarizers on the lens and polarizing films in front of the LED lights that we were using to illuminate the specimen after it was placed on the surface, so that we could get rid of as many of the reflections as possible. I would mention that we did not actually acquire the data during the placement. They didn't want to do that at that time. We did it a few minutes after it was placed, and we did it in pieces running across there. We do set by set across there, as you'll see in a minute. But these images and the data were acquired a few seconds, maybe 120 to 180 seconds after it was placed on the surface. This is what the pattern looked like on the left. You can see you can barely see the white speckle pattern scattered on the top surface. It's nice contrast. The bottom one, you see a lot more white. Those are actually reflections. And the polarizers were used to eliminate those reflections. One of the things that's required in DIC is that you specify exactly how you got the data. That's on the right-hand side in the blue highlighted table, along with the information you use to calibrate the system and the details about the lenses you used and how you corrected for lens distortions. And those are all shown in the table. We did not use any of the polarized, the non-polarized images. There were too many reflections in them due to the shiny surface of the toes. The way we did it was we actually laid down 610 millimeters of it, 10 minutes. We acquired the data as soon as possible after that. Within 10 minutes, we got the data. The toe went down very quick. We laid the whole 610 millimeters in a few seconds. As soon as we stopped, we pulled it out of the way and then started move the system in and start acquiring the images as quickly as possible. We stitched the data together using software from Correlated Solutions. The big 3D software is what we used, and the various sizes, image analysis parameters are shown. The one I would point out is the speckle size was pretty small, 0.15 millimeters on the specimen. You do need to oversample the pattern with your pixels in your camera. So we had about little less than 3 pixels per speckle in the image, and that's sufficient. You need at least 2 for oversampling, so you can accurately acquire the data when you do the analysis. Here's what it looks like. You can see we did a straight line. R equal infinity, that's the radius of curvature. This was slightly curved, 2.54 meters was the radius of curvature. Here, slightly curved more. And here was a fairly sharp curvature, like you might see around a window or a door. For the ones up here, no wrinkles were found. We saw very slight perturbations, but no sharp wrinkles. As we decrease the radius, here you can clearly see the wrinkles that are showing up. And on the right, you can see them more clearly. The pink line is shown up here as a line graph to show you the 2 sharp wrinkles we saw on the surface. So we did have wrinkles. They were not bonded well, but in between the wrinkles, it bonded well. So there's some not quite regularity, but relatively consistent pattern to the wrinkle formation on the inside curvature where it buckles. So what did we learn from this? We learned that we could acquire this data. It's possible to make measurements to obtain the data on the toe. And we could do it with the cameras by placing them in the proper location. We also found that it happened very fast. These wrinkles popped up very quickly. We'll see in the next part of the talk. And we've already been discussing how to get this rapid occurrence of wrinkles that occurs as the roller goes across and bonds it down on the surface. And one way to do that would be to bond these to the top surface of plexiglass or a thick piece of glass and look through it at the bottom surface of the toe and actually put the pattern on the bottom of the toe in a way that wouldn't affect the bonding. We're now working on this. This will be a little way in the future, but we've got some ideas about how to do it. And we can correct for the distortions looking through the glass. We've done that most recently with software. So we feel that it's feasible to actually, with a high-speed camera, to actually watch the roller put the pattern down, put the toe down, and look at a pattern on the bottom side and see how it stretches and eventually debonds. So the speed at which the images are obtained is going to be important, as we see from the FE simulations that you'll see in a minute. And there were slight imperfections on the surface, as it turns out, and they did cause, even for straight lines, some slight debonding of the toe from the substrate. But in general, those were quite small. They didn't seem to have a big effect. Turns out for that very sharp radius of curvature, 305 millimeters, we had 14 wrinkles in 460 millimeters. They're relatively regular, but not exactly. And we did find reduced wrinkling at the beginning and end when the path straightened out. So that was consistent with the straight portion. We actually did a straight, put down a straight path. We saw virtually no wrinkles. And that was the same as what we saw at the end of these toes as we went to a straight path right at the very end where they were curving. Okay, so that's the first part. We were able to show that we could do this. We transferred that technology to Boeing, and then we were asked, could we predict what we just saw? Is it possible to develop software that we could use with existing Abacus, for example, commercial software packages that would allow us to simulate? That was the next part. So we're going to try to simulate what actually occurred. And here's the simulation overview. Here's the roller right here. The roller that is used in the actual advanced fiber replacement process has an outer surface here that's made of flexible outer core, typically silicone rubber. It has a hub that's very stiff, typically steel, and an inner pin that's also fairly rigid. So the inner parts are rigid, and there's very low friction here in these cases. We vary the friction to find out how that affects things. But the goal is to take this roller now and roll it along the path shown here in simulation. And that's what we developed. As we did that, we had to had the toe coming in at the same rate that we sent it in when we actually processed it, and then use that combination of the toe coming in and the roller rolling to flatten it on the surface and then see whether or not we can predict wrinkles. And that was the idea behind it. It turned out we were able to do this. After several months of effort, we were able to develop it in a way that we could consistently predict what happened as we rolled the toes, who we have properties for, you'll see in a minute, along curved paths on flat surfaces in this case. Here's the finite element data for it. For those that are computational folks, this is an important slide. I don't want to go too quickly here. You can see that we're using a couple of 150,000 elements total. The biggest issue was with the 4 noted doubly curved shell elements. To make a stable increment in time with this explicit method, we had to use something on the order of 38 nanoseconds, 39 nanoseconds for the steps. And that was the controller for this. That's what slowed things down. If it wasn't for that, if we could go quicker, and we did the best we could to speed it up by using mass scaling, but it still took a few hours to run one simulation due to the speed that we have from this. On a large cluster, it certainly is faster, but at the same time, for what we had available, we could do it. It just was a bit slower. Here's a graphic of it. Here's in this case, we had 9,600 0.5 millimeter doubly curved shell elements. We assumed the toe was transversely isotropic. Here's the properties. Notice that E1, that's in the direction of the fibers along the length. It's very stiff. The transverse was basically the stiffness of the very soft epoxy glue and a little bit in the fibers, 2 gigapascals. And then the others are the shear moduli that we had from the literature. The Poisson ratio between 1 and 2 was 0.25. We got similar results when we did limited test ourselves, but these are what we used from the literature. Here's the geometry. It's 0.16 millimeter thick. The width is 6.35. And raised curvature this time is 300 millimeters. Here's the traction separation laws, sigma delta parameters. We had to measure these. That's the third part of the talk. We actually had to measure the energy release rate for both mode 1 and mode 2. In mode 2, we found that it was twice as strong. Twice the energy release rate was twice as big as it was here. The strength, that is the maximum tensile strength, was 1.5 megapascals, where the shear maximum was 0.35 megapascals. These we measured separately. So let's take a look at the simulation and see what it looks like. You can see as it rolls, you begin to see the wrinkles popping up down below. Notice they're not uniform. They pop up here, none, here, 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 and so forth. Very similar to the way that it was before. I'll show that one more time. So we were quite comfortable with what we saw here. This is reproducible with no difficulty. The way that we actually bonded the material to the surface is called a sticky contact option in Abacus. For those that know about that, works really well. As soon as it touches, it sticks. It then follows the stress field, and if it becomes too large, it separates again, and you can stick and separate many times before it finally actually separates or sticks permanently. Unfortunately, that happens extremely quickly. We're not able to follow that in detail yet. And that's what some of the future experiments would be about, is trying to see what happens during that time frame as this roller is rolling over and things are compressed and then unloaded and either separate or stay bonded. Last time, and we'll move on. Okay, here's the results from that. The simulations show no wrinkling, just a straight line. And that's also what we saw when we actually did this, or the simulations are in red. These are the observations. We saw no wrinkles for the others either, for the 2500 or 1250, 1260. But for the 300, 305, we did see that we had 12 and 16 wrinkles in two separate tests. This is the wavelength, the average wavelength. The distance between them is what this is. Notice there's a lot of variability there experimentally. The spacing was pretty jumped around a good bit. The width, that is the width, how wide is the wrinkle itself, ranged between 8 and 10 millimeters in width. The height of it's very small, 0.4, but quite a bit of variability. We predicted it. You see, here's the predictions. We saw 20 wrinkles when we predicted it. They were in the same range as these. The wavelength was about 14. Notice much less variability with predicted. There was some, but it wasn't that bad. We saw similar for the width. It was slightly higher this time, the distance between them. And here we found that the amplitude was higher than what we actually saw experimentally. Here's the details about the sticky contact. Mode 1 and mode 2 were developed separately. We assume the mode 3 and mode 2 are the same. That is the shear across as well as in the direction of the fibers. That may or may not be true, but that's what we assumed based on available data. We didn't see much mode 3, as you'll see in a minute. Now, this was the fun part for me. I'm a mechanics person. I'm particularly interested in how things are happening as the roller goes across. And now, if you look carefully, you'll see a little yellow, red dashed line. That's the roller position. So it's rolling along this direction. This wrinkle is already formed. This is the fifth wrinkle. And we're now passing over this spot right here. And just behind it, right here, the next wrinkle is going to form. You can barely see in the data, there's a slightly higher uplift already. As the roller moves a little bit further out, now we see clearly the wrinkle is starting to form. The amplitude, the stresses here are changing, and it's starting to lift up a bit. As we move on down, you can see that the wrinkle is continuing to form. Now it's very clear. At 1 millisecond after, the wrinkle is there. Now we see on one side, we see compression. And where the wrinkle is, as it bulges up on the top, it's in tension, and it drops down to compression on the backside. And the amplitude is increased for the wrinkle to its maximum. And here, after 3 milliseconds, it's all over. Notice the wrinkles look very similar. The stress fields before and after are quite similar. So this gave us a good feel for what's happening as the roller passes over and the wrinkle begins to form. We use the sticky contact, and here's what the stresses look like underneath. Sorry, go back up. You can see here that there is a shear on one side and going in this direction, and on the other side there's a shear going in this direction. So not only do we have uplift, that is, there's tensile load as it's trying to uncompress after the roller goes past, but we also have shear on both sides. The shears are not huge, but they are there, and they are important in the process because that on this edge is where it begins to wrinkle. Here, where the shear in this case is fairly large. Okay, more details about it. It took 8 hours for a 12-node cluster, a 1.4 gigahertz cluster. It took a half an hour for a 32-node, 2.5 gigahertz cluster to run the simulation. We found that viscoelastic characterization wasn't important. These is all happening in 1 millisecond or less. And during that time, independent data that we actually got ourselves showed that viscoelasticity was small during that time frame. The modulus only went up by a factor of 2 during that time, which means it's still basically elastic. So we weren't required to use viscoelastic concerns because of the speed at which the wrinkle is forming underneath the roller. And there is a mixed mode condition, and as a result, we are now pursuing mixed mode characterization of the traction separation laws. Because right now we have the mode 1 and mode 2. We don't know what the mixed mode is. We used an equation to approximate it. We don't know how accurate the equation is for that case. So obviously we were interested. We had to have the mode 1 and mode 2 traction separation relationships so we could run that simulation. You saw from the last slide that it has a combination of mode 1 and mode 2. So we had to do that. So we went ahead, and for soft materials, I want to emphasize what we developed here. We actually did it for uncured thermoset toes. These things are extremely soft. Some of the toes have a modulus of 420 megapascals. Compare that to aluminum, 30 gigapascals. So it's extremely soft comparatively. So our goal in this case was to develop a methodology we could use for uncured epoxy matrix with the material we had. The loads were low, 130 newtons or less was all we needed to separate these things. We developed an approach using work by previous bioengineering researchers. They were seeking to measure the adhesion of glass slides to biological materials, which are extremely soft. The glass is extremely stiff. We modified their analysis and used it here, and we reported on that in a recent publication. It works really, really well. It's much simpler than trying to go through all the work that's done for the J-integral analysis to get that data. And even in some cases, we couldn't use that because some of the boundary conditions for the J-integral were not known due to the extremely soft nature of the material. Here's the specimen. It's a standard old specimen. Those that have done adhesion before will look at this and just smile. It's been around for a long time. We call it the old double cantilever beam type specimen. You can see the top specimen is called an adherent. The bottom specimen that is going to be bonded to is an adherent, and the adhesive layer is in between. The geometry for this, we have various parameters here. The A0 is the unbonded length between where you're loading it at the hinges and the initial bonded position of the adhesive layer. The shims were important here. I want to emphasize that. If you don't put the shims in, this stuff is so soft that when you put the adherent on, it'll just squish it. So you have to put the shims in, hold it apart until you're ready to run the test. Then when you run the test, you can get the load slightly up and pull them out, or you can just run it as it is. The shims are very easy to pop out, and so they don't cause a problem with transferring load once you're ready to go. So we simply removed them right as we started the loading. The analysis, I'm not going to bore you with. The equations are here. The opening displacement is V. For rigid upper adherent and rigid lower adherent, the equations are relatively simple. You see a bunch of angles that we measure. The stress is easy to calculate from below. It's not difficult here. The stress is a function of delta N is obtained in terms of the load P, and a variety of parameters involving the derivatives of the displacement. The neat thing about DIC is that we measured delta NC and delta N during the experiment. So we have all the derivatives directly from the data. So all the stuff that you see here, the angle, the theta, delta NC, delta N, all those are measured. L and A are known from the initial geometry. So we calculate V of X and we directly calculate sigma. because we also know the load. So everything here is relatively simple to calculate. No need to do j-integral analysis for it. If you do it in shear, that was mode 1, much simpler, typically, except the very ends of it. We did the final analysis to verify it. When you shear something with delta T over 2 on the top and delta T over 2 at the bottom, the shear displacement, the stresses are essentially uniform along the length, except the very small areas near the end, where you have the well-known increase in stress due to the singularity there. But it's a very small region, and we found that it had very little effect on our data at all. The vast majority of it, since that's a small region, works out fine. So you simply use an average stress, and you measure delta T during the displacement. You know P, so you can directly calculate the shear stress and the shear displacement, so you get the traction separation law directly. Here's what it looks like when we did the mode 1. The pattern specimen you can see on top is painted white. The adherents were to measure the rotation angle, theta, and all the displacements, of course. And in addition to that, if you look carefully, you can see we're ready to do mixed mode. We just haven't got to it yet. We have a semi-Marcan specimen that this is attached to. But we've only done the mode 1 and the mode 2. That is the pure opening on the end and the pure shear. In the pure mode 1, you see on the bottom right a figure that looks like there's guy wires between top and the bottom. That's the uncured epoxy. The stuff is so soft, it stretches out into fibrils, is what they call them. Those that have worked in this area are well aware of this phenomenon. There's virtually no load carrying capacity for this, but it is interesting to see how it stretches out across there. As the material becomes harder, those fibrils go away and it becomes much stiffer. Here are the two traction separation law starting points. This is the force and displacement for mode 1, the force and displacement for mode 2. We took the derivatives, as we heard earlier, of the various curves here. And by doing that, we end up with the two traction separation laws. They are totally different. You can see that. There's no real comparison here. The mode 1 goes up fast and then dies, almost an exponential drop. The mode 2 is a parabolic curve. The data, you see multiple lines, those are repeat experiments to show the type of repeatability we get. And repeatability is pretty good. We're fine. We're okay with that. So this is the data we used in the model that you just saw. The importance of this is we can do this now for other modes, in addition to mode 1 and mode 2, and see how the mixed mode combination behaves. But we just haven't got to it yet. Kind of a summary of all this in this case. We did all the experiments at 25 degrees. We can do it at 35, 40. We can put it in a small oven. Everything works fine in there. We just haven't done that for these cases. The fibers in the toes are along the length of the toe. We have not crossed over and put in toe that goes across the width. That's to be done. It's a bit tricky, but we're trying to figure out how to do that the best way, because there are length effects in the toes in these fibers. If they're too short, the behavior may be different than if you leave them together and just bond it over a certain length. But we haven't done that yet, so that's to be done. We were confident with the simulation predictions that we transferred the simulation to Boeing, and now they have it to see what they think, how they're going to use it. So that concludes the first three parts of the talk. The next one is totally different. This started, I explained to Professor Jacoby that this work actually started from a query from the government about could we do this to measure specific things on railroad tracks. that's where it kind of began, and it's evolved since then. What we'll show today is its initial applications for railroad tie. So, in a broad sense, there are regions of infrastructure under bridges and along railroad tracks that you need to inspect on a regular basis to ensure that they're going to be safe. Typically, they're done by humans, and it's time consuming. And when you're trying to get under a bridge that's 500 feet above a river below, it's not particularly safe. So unmanned systems, if they could be designed and developed appropriately, would be good inspectors for those locations. Most applications today with drones are global images. They look at a large area, like the state of South Carolina or Illinois, and they draw conclusions about what they see in a bigger sense, over several hundred miles potentially. And they look at subsets of that, but on a much broader scale. What we're talking about here is changing that by using very localized drone applications where we look at images of very specific regions at high resolution. Here's a typical set of drones. Professor Nikos, I'm not even sure how to say his name. We call him Nicholas V, because it's a name I have very great deal of difficulty pronouncing, from Greece. Nicholas brought over a series of ideas. He's developed his own quadcopter and quadrotor program at the university. He has a variety of them with gimbaled cameras. The gimbaled cameras is extremely important for what we're doing. We can rotate the cameras to where we want to look at whatever region is of interest. They have onboard computers, and they have the ability to handle a variety of payloads. None of his copters are currently for large payloads. They're small to maybe low medium size payloads. A few 20 pounds is max that he can handle. Right now we're only handling 4 to 5 pounds. Here's the one we used in our work. We used, without getting into, those of you that are drone fanatics, you're going to like the first line. For me, I started on the second line, StereoDIC system. Yes, we used a small 2 megapixel cameras. Those are not very not high resolution at all. They're low resolution, but they work fine for this particular application. We used f1.4 lenses with a focal length, which is a wide angle lens, 12.5 millimeters. We used a rigid beam. There's a carbon fiber. We had to manufacture it because it had to be light for this particular copter. We used a compute stick computer on board as a frame grabber for the DIC system. The angles between the cameras are 15 degrees, and right now they're about 0.3 meters apart. We can keep, with the onboard PID controller, we can keep the drone within plus or minus 20 centimeters of the position we want, which was more than adequate for these cameras because they're such wide angle. We keep our area in field of view. In our case, we're going to be looking at the railroad ties you see on top. Notice that these are not rectangular. They actually have an odd shape to them. They're actually reduced in size in the center and larger on the outer part. The yellow dotted dashed region is where we'll be looking with our data. We don't look at the outer parts of this. They're not of particular interest to us at this point. It is pre-stressed concrete. It is pre-compressed during the manufacturing process, and this one has 8 steel components inside that are unloaded when the concrete has dried, and when they unload them, they were in high tension. You release the tension, and the whole thing goes into compression. You have to do it carefully so you don't crack the concrete. It's well established today how to do it. And that's what the line looks like, bottom right. You can see all the railroad ties in place. Here's our test. It's a photograph of the 4-point bend setup. The heavy load is the white arrow at the top. It's actually applied to the beam at 2 points, shown by the downward yellow arrows. And below are 2 upward contact points, shown with the light yellow arrows. Everything is mounted on 2 huge concrete blocks, as shown in the bottom right. So we're going to look at that. And here's a video. Now, there is some, I left this at 10% of the volume. We had to wear ear muffs because it's extremely loud, but I want to play it at 10% volume so you can hear what it's like. During this time, it's acquiring data. Every time it flashes, an image is acquired. There's not much else to it. You can hear people in the background talking, but in essence, acquiring data, and when we're done, it comes down, it drops on the ground, and we acquire the data from it and analyze it. So the experiment was done 4 times. 4 different beams were analyzed this way. If you notice, this beam is upside down. It's actually in reverse bending. They did that for reasons related to the integrity of the beam structure itself. You want to know what happened if it went in reverse bending, as well as normal bending that it gets in the field. So go back up. So when we loaded it at a rate of 0.37 kilonewtons per second, or I'm sorry, 0.083 kips per second. It was for continuous image acquisition. Battery life was 12 minutes for this, but the test took a lot longer than that. So we had to drop the drone down 3 times, change the battery. We held the load for 10 minutes during those changing the battery and return to flight time period. We acquired all the images at constant load before we ever started as a baseline. Synchronization was of the multiple sensor systems, loading, imaging, LVDT sensors were all performed manually. However, all the images were acquired simultaneously by the VIC software. It's critical that you do that. This thing is moving around in space. You saw it. So you have to acquire the images simultaneously. Otherwise, you're going to get erroneous data. Here's the results we got from the drone. That was the one on the front face, which is the rectangle. That's the bottom one. The stationary DIC on the back face is the small triangles. And the LVDT at the center line is the black ones, which match really well with the front face, where we got the DIC data. So we're quite comfortable that the drone is giving us the right data. The load is on the far right for this case. Deflections are at the top. Here's what it looked like, front side and the back side. These are all cracks. These are not, it does show things that look like strain. Those are pseudo strains. The cracks are opening up. Those are not real strains in the material. It's a really good way to see where cracks are forming. The bottom shows confidence intervals that come from the software. Confidence intervals indicate that there's a poor correlation where it's red. And you can see where the cracks are. It has poor correlation because there's no pattern left. So it just indicates, and that's another way to indicate where cracks are forming in the material. But they're consistent on the front and on the back. The stationary system and the front system gave similar results for this axial strain, which is a bit erroneous because there are a lot of cracks in here. So, modified small scale system has been shown to be capable of acquiring the data. There are a variety of things that have still got to be done. That's in the second part. The optical filters are going to be needed outside. We're going to have to figure out how to do on-the-fly calibration. We think we know how to do that now, but we got to do that and show it. How much rain and wind and conditions can we handle with a drone like this and still get accurate measurements to be determined? We don't truly know whether we can do this under a bridge that's over a 500-foot deep gorge if you have winds that are 50 miles an hour going down the gorge. We have to figure out how to handle conditions like that, or whether it's even feasible. But there are a variety of cases that we know are feasible already. It's just there are some that are going to require more work. That's it for the main technical part. Brief tidbits. I was asked to give a little bit of history of DIC, so I'll do that. For those that don't know much about it, the actual first when I wrote the book on image correlation in 2008, 2009, I discovered that Gilbert Hofbrauch was the first known person to try to perform digital image correlation. He did it a totally different way. He did it in 1957, which is way back as far as this technology is concerned. The way he did it was he scanned two pieces of film that were obtained from a plane flying high in the air. One was directly over a target, one was further out from the target, but he still could see it. He stored the images in digital format after he acquired them from the film. He tried to compare the digital forms in hardware to measure the height of the ground. This was the way that it originally was done in the photogrammetry field, which is where he spent most of his time. He used an analog plotter to show the height. It was really interesting. And it was done in the field of photogrammetry. There's a Society for Photogrammetry that does an incredible amount of good work. And that was one of the places that he spent his time. So that area, though we attempted to do it, it did not continue with that work. He moved on to other stuff. So the 2D DIC was conceptualized in '79, developed and successfully used in '82 at the University of South Carolina. Initially started at the University of Illinois. Some of the first ideas came in the old TAM Theoretical Applied Mechanics Department in '79. But the colleagues at South Carolina took it on, and fortunate enough, I came down to work with them. They used 35 by 35 square pixels. Took 30 minutes on a VAX 11780 for 1 point. Today we get 100,000 points per second. So the world has changed. The first stereo experiments, which is what the drone was using, were done in '88, '89 at the University of South Carolina. Charlie Harris at NASA was the person that was the impetus for developing the field system, field-capable system. Was used. Most of the work was done between '82 and '99 in South Carolina. The first experiments were done between January 30th and February 5th of 1995 in Seattle, Washington on a Boeing 727. They did not pursue it, but Claire Paul and Scott Fawaz at the Air Force Research Lab felt it was important to do it. And so they asked for us to develop the system, and that's why Correlated Solutions Incorporated was founded, to transfer the technology to them. Neither NASA nor USC wanted to do it, so we decided to go ahead and do it. And the last slide. Today, CSI is the only US-based correlation R&D center. And that's, if you want to look at the stuff, it's at that location. Here's the various articles. I've sent a copy to Professor Tahir Saeed. You can get a copy of this from him, and you can look those up if you're interested. And as the last slide, here are some of the slides over my career. On the bottom right, I kept this one out, especially. That's my advisor, Chuck Taylor. He was a National Academy of Engineering member from the University of Illinois. He retired in 1980. He was my advisor. I graduated a year after he retired. Thank you. And I'll be happy to take any questions. Not sure if Roberto's going to do it or Shelby or whatever, but that's it for the talk.
So there are a couple in the Q&A, Roberto, if you want to start there.
Yeah, okay, yeah. Let's start with the Q&A. So I have a first question from Shashank. So the question is, what experiments were used to define the viscoelastic material model in Abacus? Slide 18. He's referring to slide 18.
Okay. I don't know how something happened here. Let me go back to that. I'm not sure how I did it. Hang on a second. Huh. Interesting. Where is, there it is. There we go. Okay, 18. There was no viscoelastic model. I mentioned that earlier. We use the elastic conditions because the deformations during the wrinkle formation process were elastic. We were able to show that. We did the simulation. We did the experimental work to get the viscoelastic properties, and we published a paper on that. And we showed that the viscoelastic properties were only slightly changing during the wrinkle formation time. So we decided not to utilize that during that part of the simulation. So we didn't use it at all in the simulation because we're primarily concerned with the wrinkle formation.
Okay, there's another question here in the Q&A by Youngmoon Lee. So they say in UAS, I think applying absorber to reduce vibration and maintain position of camera can be quite helpful. Is it acceptable or a considerable method?
Absolutely acceptable. We didn't show it there. The cameras are mounted. I apologize for not showing that. The cameras are mounted exactly as the person thought. They're mounted on vibration isolators. They're very small, they're very thin, but they do a really good job of isolating the vibrations. As the drone is moving and vibrating, it doesn't handle the motion. This motion, it goes with it. But if there's vibrations caused by the rotors, those vibrations are damped very, very well by the vibration isolation pads. So yes, they are there, and they're extremely useful. Without them, we saw a lot more noise in the data.
Okay, I see there's a raised hand here from one of the panelists. Oh, it's Professor Nancy Sotos.
Sure.
Do you have any questions?
Hi, Mike.
Hi, Nancy.
Thanks for a great talk. I have a couple questions, if I can indulge myself. First question is back at the beginning of this section you're showing. And you showed, I think very early on, you showed the speckle pattern on the layers of the toe placement. How did you get that speckle pattern on there?
Okay, so we unroll. This thing is on a huge roll. The roll is about a meter in diameter. And on the outside of that, they rolled onto it for the AFP system. This system, Nancy, is a industrial system. It's 9 meters long by 4 meters tall. It's huge, and it's 6 meters in width. So it's too big for true simple research application. It's an industrial production environment system. So we had to work with that system, and it has massive rollers on it. We roll onto that the toe. So what we did was we rolled the toe on, and we got it ready, and then we unrolled it back off for the part that we wanted. We then laid that out flat and put it in slight tension on a mandrel that's beside the roller. We then spray painted it very lightly with black spray paint. We used high temperature spray paint you use on automobile manifolds. It's an
Because
automatic-
the tell, I assume, is basically black as well, right?
completely black.
All right. So you
Yeah,
did
but
black on
this is-
black.
No, white spray paint.
Oh, what? Okay.
So
Got it.
all you're doing is putting the white dots on.
Got it. Okay.
Yeah, but the white spray paint was manifold paint because this thing does get pretty hot. When it's heated up for that very brief time, it's only heated up for a few milliseconds, 40 milliseconds, 50 during the time it's placed. During that short period of time, it gets hot. We didn't want the paint to be damaged, so we used a high temperature paint.
Right. Thanks. Because I think that's very challenging in some ways to get the measurements on something so thin. And you're always looking from the side of this large part, right? And identifying the wrinkles through, like you're looking at the thickness direction all the time, correct?
No, absolutely. We're looking at the top. We're using StereoDIC.
Okay, so you're just looking at the top of this.
Top, that's the part we patterned. We patterned the top surface of the toe. And then it was placed out on the surface. The bottom is bonded down and we're looking at the pattern on the top. And as the bottom separates, it bulges up and we measure the bulge on the top caused by the delamination, the separation on the bottom.
Okay.
So we're actually measuring what happens on the top surface of the toe as it debonded on the bottom.
Oh, I see. Okay. Thanks for
That's
important.
No, yeah, we're not looking from the side. It's too thin.
Okay.
We were going to try to do that, but once we found out how ridiculously thin it was, and the fact that this thing we put it on at like 0.6 meters a second. There's no way. Thing is too thin. It's high mag. There's no way we could do it.
Okay, so we're just looking at the width of the entire tape.
That's correct. All
Got it.
the way across. That is correct. That's right.
Good. And then just sort of a comment on the where you were measuring the fracture toughness between the layers in the middle part of the top. Have you ever thought about applying that towards like printed structures where looking at the toughness between, like a traditional additive manufacturing process where you have polymer layer 1 and polymer layer 2, especially if it seems like it's an interesting geometry for that you've developed.
Yes, we've actually done something with one of our 3D printers in house. The difficulty with this, it's a difficulty, but it's also a positive, is if it's as you know, if you bond them together and they separate on the interface, everything is copacetic. Everything works. The theory and everything is fine. If you bond them together and the bond is strong enough that it requires all of the material to begin to fail together, then the energy release rate is a function of the thickness of the two materials. Mm-hmm. And Savone showed this at Cambridge in 2007 and 8 in two beautiful papers, where he showed if I separate on the interface, everything is consistent. If I separate because it starts trying to fracture both sides, then if I vary the thickness of the sides, if I normalize by the thickness, I get the same answer. But if I don't normalize by the thickness, I don't get consistent results. It's like it's a volumetric failure process when you actually fail all of the material in those thin layers that you bond together. We don't have that with the toes. Why? Because the upper part of the toe is a very stiff, strong, composite, fiber-rich region, which won't break. So if it's going to separate, it's only going to separate right there in that very thin interface.
All right, good. And then my last question is on your final slide. Who's in that baseball picture?
Baseball picture. Hold on. Last slide. Baseball picture. I'm checking. There's Chuck.
I know that.
No, Chuck. Come on. There. Baseball picture. Oh, that is me at the age of 9. Right there. That ugly looking guy in the dead center with the bat It's right before I struck out is right there. Yep. It's the only picture I've got from that time sent to me by one of my classmates about a week ago.
Nice.
Yeah.
Thanks.
Yeah, sure.
Okay, I see Professor Saif also raised his hand, so you can ask your question, and then Professor Yashik after.
Yeah, Mike, very nice talk. Couple of questions. What
Sure.
determines the delamination gap or the buckling gaps when you're bending the specimen?
Say it again. Which one are we talking about?
In the first part of your talk,
Okay.
when you did the simulation,
Right here.
yeah,
This part.
as well as the experiment, they seem
Yeah.
to have some correspondence. So I see the buckling popping up.
Yep.
And there's a lot of variability. Is it some of them are close by, some of them are far apart?
Yep.
Any insight on what's the mechanics here?
Yeah, we believe, and it's just purely a belief at this point, that this is a function of the way that the sticky contact is working, and the way that the simulations have been performed. We don't think that is truly the way it has to be. We think it should be uniform, but it's not.
Yeah.
We've run this multiple times by varying some of the parameters and get it become more uniform. Whether you want to characterize it as issues with the convergence of the solution, or whether it has something to do with round off error or other things, we're not 100% certain. So I agree with you. We thought it was going to be uniform, and as you can see from the data, from the simulations here, the wavelength is fairly uniform, but not that good. I mean, it shouldn't be that much. It is that much variability at all. We have some of them that are several millimeters off, and we don't know why. Experimentally, I can understand. I don't have a problem with the experiment. The experiment, the way we run the experiment, the roller itself, variability in the substrate, all those kind of things can affect it, and that's why I think it's extremely large here. But even now, these are still too big. But we don't know why. We don't honestly know the details of why it's as big as it is.
Okay. Last question here is that the idea of using the drone, when it is in the flight, it's not very stable, right? So you have to do the drift correction.
Not for strain.
Not with strain. Okay. Yeah. Yes. But
Yeah.
thank you.
We like non-dimensional parameters. As far as the drift correction, let me go back to one thing that if you look carefully, you'll see something. I didn't show it at the time, but I'll come back to it. We'll see it in this picture. Look right down here at the very bottom. What do you see? You see a pattern.
Yeah.
This pattern is a rigid digital image correlation pattern, a much bigger pattern. We can use that as markers to recenter everything.
Yeah.
Move things back. And that's what we did. We used that. If you really want the displacements to be consistent, we used them. We transferred them back to a common coordinate system.
Yeah. Very simple, but very elegant.
Exactly. Yeah.
Thank you.
Sure.
Okay, now Professor Yashuk, you can ask your question.
Hello, excellent presentation and a great overview on the technique. I have a couple of general questions about the DIC technique. So one is, what are the guidelines for imaging heterogeneous materials in the DIC technique? You showed two examples. One was a composite, one was concrete. And these materials are heterogeneous. So what advice would you give for users how to handle heterogeneity of materials in this technique?
Yeah, it's a really good question, particularly when you have substantial differences in modulus. The recommendation that most of us have is to try to maximize the spatial resolution. That's a bit tricky in this case. When you maximize spatial resolution, you reduce the subset size, or you increase the density of pixels that you're using. Like there are cameras today that have 50 megapixels. They're massive. So you can put a very small pattern on, and you can still resolve it at very high resolution with modern 50 megapixel cameras. So the only downside to those cameras is you can't go very fast with them because it takes time to store the data. That's one thing. Second of all, when you do that, those cameras themselves, it takes longer to analyze all the images, and that is true. But the latter is not as big an issue today. So my suggestion for heterogeneous materials is use as high a resolution of a camera as you have available, and to use as small a pattern as you can. And once you have those together, use a typical small subset size to get the local response of the material. And that local response would be on the size of the subset. Typically, you'd like to use as small as a 25 by 25 subset. It's about as small as you can get and get the most accurate answers. If you do that, and you're in a 25 by 25 pixel subset, say occupies a 0.1 millimeter by 0.1 millimeter area, then what you get is the average response over a 0.1 millimeter by 0.1 millimeter area. And as long as your heterogeneity is on a longer wavelength than that, then you should be able to pick up the effect of heterogeneity. So your subset size on the specimen dictates the wavelength of variability and heterogeneity you can measure. So if it's a 0.1 millimeter by 0.1 millimeter subset, get the average response there. Then if you move over and do two more, then you're covering a 0.3 millimeter area. And if you have 3 data points in that, assuming they're completely discontinuous, you can actually overlap them, but you don't have to. Then you would get the variation over a 0.3 millimeter length reliably, because you have enough data there to do that. You can move in small steps across there and get the average response on each area, 25 by 25, over that length. But again, the lower limit is going to be that 0.1 millimeter. You can't measure things that are happening faster than that because they're embedded in each subset and they're averaged out. I hope that helps.
Yes, thank you. Is it written down somewhere, or studied in more detail?
There is. If you get on there is a best practices guide. You can get on. There's a society that developed a best practices guide for how to use DIC. I was president of the society when it happened, and they published it separately and it's available online. It's a PDF to anybody who wants to download it from the International Digital Image Correlation Society website. So if you go to that website, you get on there, you'll find right away the best practices guide is a PDF that you can download. It gives you a lot of information about how to use DIC correctly. This particular issue, to be honest with you, is a higher level of expertise. They may or may not directly address that, but they'll address most of the things that are important. And if there's other things that you run into, of course, you can always contact me. I'll be happy to help you.
Great, thank you very much.
Sure.
Yeah, because the issue too is that this heterogeneity can be subsurface, right? So, and how far subsurface it is will contribute to the results.
Sure, that makes it much more difficult. The DIC, of course, is only the surface measurements, and as a result, there's obviously could easily be some non-uniqueness in defining the subsurface defect size and position that would give you the surface response. There's an inverse problem. It may be uniquely determined in some cases. I'm not certain, but at least this will give you a feel for what you would need to do to get the surface heterogeneity reliably predicted.
Thank you very much.
Yep.
And thank you for useful hints on the chat.
Sure.
Okay, there's a final question from an anonymous attendee. So they ask, is there any variation in the wrinkle wavelength with respect to the roller speed?
Yes, there is. But it's not big. We only ran it for 3 speeds. We ran it at a slow speed, 0.1 meters per second, 0.4 meters per second, and 0.7 meters per second, or 0.65 meters per second, something like that. Now, we found a very minor change in the wavelength. There was a small difference, but it wasn't much. The biggest problem we had, to be honest with you, with doing different things is the toe itself is an uncured thermoset resin. And the longer it sits out there on that roller, the more it stiffens. Okay, it's called aging. It's not curing per se, but the chemical processes have started. So when we saw these slight differences, you know, this thing takes 2 or 3 hours. So this thermoset resin toe is sitting out in air, room air, at room temperature, 2-3 hours. So it's aging. So we don't know whether what we saw, the differences, were directly caused by the speed or by the change in stiffness of the toe. And as a result, we never really reported it to Boeing, but we didn't attempt to report that in literature because we couldn't separate them. It's not a good idea to just say this is what happened, but we don't really know for sure, which it was. After 2 or 3 hours, it begins to change. We can see it. If a student goes over and picks up a thermoset toe after it's thawed, it's very flexible. If you wait 3 hours, you pick it up, it's not as flexible. It's already beginning to change its properties. So that's just a sidelight of why we didn't talk about it. We did do it, but we didn't do it in a way that was directly interpretable. We used the same toe that was on the roller. We ran it 3 different speeds, but they took time to get the data for each of the 3. And as you can see, over time, things are going to change, and we didn't know which was, since it wasn't a big difference in toe wavelength, we weren't sure which was the primary cause.
Okay, well, thanks everyone for all your questions. Thank you very much, Professor Michael Sutton, for this great talk. And I don't know if
definitely put a message in there, since there's no, clapping that we can do, but just toss a thing in there or something
It's okay.
with this virtual environment. And we'll thank Professor Sutton one last time.
My pleasure. And
Thank you.
hope the semester goes well.
Thanks so much, Mike. It was really good talking to you today. I have to take off. I don't know if anyone else is sticking around.
Yeah, that's fine. Anybody
Yes,
wants to talk,
thank
I'll be around. If not, you guys take care of yourself.
All right.
You did a good job, Roberto. Well done.
Nice work.
Yes.
Oh, yeah, thank
Great
you.
job.
Well done.
Thank you.
Thumbs up.
Thank you. Great talk. Thanks a lot.
Take care.
You too. Bye.